Thank you, Jennifer. I'd like to introduce two more graduate students, Tyler Schott and Kevin Westhoff. I had the benefit last year to see them work on this project that they're about to present to you. It was pretty cool to see it just build more and more in complexity. And I was a sophomore at the time. I just remember thinking like, wow, these guys are smart. And it kind of encouraged me to keep going with all those basic classes and everything. So without further ado, here's Tyler and Kevin. I think that's why Ben was having some issues. There we go.
All right. Again, welcome to this event, and thank you all for coming. My name is Kevin Westhoff, and this is Tyler Schott. And we're going to spend some time talking to you about our past year in the mechanical engineering program, and specifically our experiences in senior design. So before we begin, I'm going to give a brief background on myself. I'm from Colorado Springs, Colorado. Over the course of my undergraduate career, I had internships with Wolf Robotics here in Fort Collins and Cummins out in Columbus, Indiana. I am a recent graduate this past May, and I'm now a master's student studying under Dr. Todd Bandauer, specifically on the thermal management of lithium-ion batteries. And so if any of you heard about the news, about a year ago in January timeframe, Boeing had some issues with their battery packs, which they, in my opinion, and Dr. Bandauer's opinion, haven't been fixed. And it's a huge problem, limiting the use of these batteries. And it's kind of fun to attack that from a mechanical engineering perspective.
So my name is Tyler Schott, and I was born and raised right here in Fort Collins. I didn't go very far for college. I graduated this past May with a bachelor's in mechanical engineering. During my undergrad career, I had an internship at Sundyne. They're based out of Arvada. They make a lot of high-speed pumps and compressors, so more of the oil and natural gas industry. I liked CSU so much that I decided to stick around for my master's degree, and I'm currently working in the CFD and propulsion lab under Dr. Chen-Feng Gao. My research is focused on a computational analysis of a pressure relief door. So these doors operate on aircraft in various capacities. I really enjoy it. It's a project with the Boeing company, and it's a unique project to have that industry sponsor. So Sue asked Kevin and I to talk about our experiences with senior design. And before I get started, I want to say thank you all for what you've made this program, what it is today. As a mechanical engineer, we really have the benefit of being able to go into just about any industry. You can go from aerospace to HVAC to automotive, and really excel in each of those. And we see a lot of that diversity reflected in our senior design projects. Just last year, we had a composite 3D printer. How cool, this 3D printing has really taken off in the past couple of years. Now we're introducing fiber reinforcement. And then we look at the aortic heart valve. This is a really hardcore biomedical project and something that could one day save our lives. And a really cool thing about this project is it really fostered a lot of collaboration between biomedical engineers, mechanical engineers, and chemical engineers. And that's something I think you're going to see in industry. And then EcoCar, hydrogen fuel cell hybrid. That's pretty cutting edge as we move forward in kind of the energy crisis. Hopefully a lot of you guys were able to check this out. Overall, last year, though, our senior design class had about 135 students and roughly $230,000 in funding. And when I first heard that number, I was like, wow, that's huge. But that value is really important. Kevin and I worked on a project that we'll talk to in a moment that we did have a little bit bigger budget and allowed us to really push the envelope of engineering. And it's cool to see CSU and the work that Dr. Stanzlowski's done to secure projects that are top-notch and make CSU one of the top universities. So as I mentioned, Kevin and I worked on an industry-sponsored project. We were on the Woodward Composite Air Valve project. We were tasked with developing a functional prototype valve. And with that, we were going to integrate an actuator internal to a butterfly plate and look into manufacturing a composite valve housing. And this particular valve is used on a GE engine. It's called the LEAP engine. They actually just successfully ran a bunch of tests on it. And this engine is used in the next generation of Boeing aircraft. So primarily the 737, or the Airbus A320. And so these are single-aisle aircraft, something that you would fly from here to, say, LA. So what does this valve do? So this valve meters bleed air over the turbine casing. And so what does that mean? So bleed air is air that we're going to pull off, in this case, just past the fan. And we want to control the thermal expansion of the casing. And why would we want to do that? So there's, between the turbine blades and the casing itself, there's some sort of gap. And if you have somewhat of an idea of how turbines work, or compressors work, you know any gap that you have between the blades and the casing is lost efficiency. So if we're able to control the thermal expansion of that casing, we're able to increase the efficiency of the engine. And that's what this valve did. So the motivation behind the project was really twofold. One, we wanted to investigate composite materials. The existing designs, as you see here, were manufactured out of aluminum. We wanted to transition to some sort of composite. Also, we wanted to increase the reliability. So the two valves that you see here, one is a linear actuated valve and the other is a rotary vane actuated valve. And these particular actuators are then coupled to a butterfly plate. Well, that coupling is subject to undetected failure. It's called latent failure, and it's a really big problem. And so we were tasked with, if we can eliminate that coupling and integrate those actuator components internal to the butterfly plate, we can make a valve that's much more reliable and much more attractive to potential buyers. So our project was really split up into two components. So as you can see on the image on the left there, we had to integrate those actuator components. And with that, there's a lot of challenges. There's a lot of small parts and everything has to fit and work together. And we were successful in doing that. We also manufactured a carbon fiber flow body. And that had several challenges associated with it. Kevin's now going to talk to you some of the tools that we used to make this project a success.
So I guess I get the part of being a nerd at this presentation. So here we go. Our design process utilized extensive engineering software, none of which was available 100 years ago. In fact, based on how many analyses we ran, we probably would still be calculating all of our solutions hundreds of years from now. So that's pretty cool. So I'm going to touch on these individually and show you how it made our project what it was. So I'm going to start with computational fluid dynamics, and this was really Tyler's specialty on the project. And what that allowed us to do was actually take a physical, and not even a physical geometry, but something we created on a computer, a design, started with a hand calculation, and we were actually able to simulate flow in it and validate if it was going to be acceptable for the flow rates that GE wanted to see in this valve. And you can see there on the graph on the right, it was actually really close, and that saves a lot of time in engineering for the tooling as well as manufacturing when you can just do this on a computer. The next was finite element analysis, and none of these are necessarily the most accurate techniques, but if you define the most conservative analysis that you can glean a lot of information out of it in your design. Specifically are my wall thicknesses going to be adequate? And what is my safety factor under this worst case loading condition? And again, this is all with, done with computers without even investing anything in tooling and manufacturing. And here is CAD and CNC manufacturing. And this is one of the most complex parts that we had to work on in design, which is called the stationary shaft. And this is a critical component of the actuator, and that red and blue passages, those are for fuel lines to hook up and actually provide the power to actuate this valve. And you can imagine the struggles you would have trying to talk about that part and all of those different clearances of the fuel passages without actually having a 3D model to manipulate and talk about. I mean, you can do your best with drawing, but good luck with everyone understanding what you're talking about. So that was a huge part of our project, was enabling this collaboration through CAD. And then came time for manufacturing. I know some good machinists, but I don't know if you can make that one, off the fly. You're going to need some computer help, and that's what we're able to have with CNC manufacturing. Computer numerically controlled within, the assembly tolerances that we mandated for this part, and it was done the first try. So that's pretty incredible. Next is 3D printing. So if you all have on your table these little green tags, that's courtesy of the 3D printing lab here. And 3D printing, as many of you know as engineers, is awesome. So you can test your design without investing in tooling and manufacturing, and you're able to actually predict issues that are not evident in CAD. So you can actually hold your design, figure out what's not going to work. I don't like how that twists in there. I can't get my hand into there. I can't fix that. So you can change stuff really fast. Rapid prototyping, it's very incredible, and we were able to use that with Woodward and CSU. And lastly, I wanted to talk about composite materials. And these have really gotten a lot of attention in the last 15 to 20 years because they have a high strength to weight ratio. BMW's come out with a new car called the i3 that has a full carbon fiber frame to it. And, with Boeing 787 Dreamliner, that was, primarily a composite aircraft. So you can save a lot of money in fuel if you're able to make your particular device a lot lighter, and that's kind of the goal of what this was on the valve. We were able to use carbon fiber here to tailor it to the expected loading that we were going to expect. With the help of Dr. Radford, I'm not going to lie, I had no idea how to even begin to break that down into something you can analyze, but nonetheless, with the numerical simulation we were able to run, we were able to predict and validate our strength of our composite valve and actually save about a pound on this overall assembly, which is roughly $800 when you put this thing on an engine. So, a 1 pound makes a big difference. So in the spirit of the evening, we thought it'd be kind of fun to contrast the times for mechanical engineering then and now. And so you can see there on the left, those are two pictures that have been on this slideshow that's been constantly scrolling. And, those gentlemen, they're working on an engine. And back in the day, I can't speak for, all the people that knew the intricacies of this, but my guess was they were working on reliability and keeping that engine running consistently. That was their goal. They didn't necessarily care about emissions. They didn't care about perfect tuning on everything. Nowadays, we do care about emissions. We do care about the environment. And you can see there with EcoCar, and that was the car out front, it has 3 fuel cells in the front of it, and it's got a battery pack powering the rest of it. So those fuel cells are actually continually charging that battery. And if I'm not mistaken, I've talked to some people on that project, that's the only design of that car just about in the world. I don't know, Dr. Bradley can correct me on that, but it's gotten a lot of attention. It was the only one at the competition. It's a very, very cool thing that CSU had going for it. And before I go to this next slide, I want to just say that we like to poke fun at civil engineers. That hasn't changed. So, you can see back then to what they're doing now. They really did backbreaking work back in the day. You can see, that guy's the particular civil engineers on the oval. He's hunched over. And with recent advances in technology, they're actually able to make those tripods a little bit more tall so you can stand upright. So, it's, saving lives, saving backs. Civil engineering is making a difference. So, no, they do great work, and it's always fun to poke fun at them. So, as I close, I just want to say thank you very much to everyone that makes this program what it is, whether that's our industry sponsors, Woodward with Sean Pollock and Robert Rusinski, if there's any Woodward gentlemen in here that know, they did a lot of work with our team in supporting us, as well as all the professors here that work to make senior design what it is, the rest of the curriculum as legitimate as it is, and all the faculty past and present that have really, really put a lot of time and thought into making this program what it is today. So thank you and enjoy the rest of your evening.